Hey, welcome to the Electronics Lab. In this video, I'm going to give a brief overview of negative feedback and include a few examples from a range of applications. This block diagram of negative feedback is a very control systems type of diagram, and we will come back to it later in the video. A more generic block diagram might look like this, which is showing negative feedback that occurs when some measurement of the output of a system is used to adjust or maintain the system within a range of values and can reduce fluctuations in the output caused by internal or external disturbances. A more concrete example of this negative feedback block diagram is to consider a home environment with an air conditioner. The temperature measurement of the environment is compared to the desired temperature, and if the temperature is too high, the air conditioner turns on to bring the temperature back to the desired value. Negative feedback is widely encountered in both the natural and the manufactured world. And humans use negative feedback both in automatic biological processes as well as in our conscious interaction with the world. For example, your body has systems in place to make sure your blood sugar levels are maintained within a desired range. Humans require about 4 grams of sugar in their blood for normal function. And if blood glucose levels drop too low, you may experience lethargy, brain fog, irritability, loss of consciousness, and even death. And if blood glucose levels are too high over the long term, that can lead to health problems like heart disease, kidney, nerve, and eye damage. A healthy person's body has homeostatic mechanisms to keep blood glucose within a narrow range. In our negative feedback block diagram, blood sugar control looks roughly like this. Blood sugar levels are constantly being monitored, and if they get too high, your insulin levels go up to bring the blood sugar back down. If the blood sugar gets too low, your body releases glucagon to bring blood sugar back up. Obviously, this is a very oversimplified diagram, but it gives you an idea of the work of negative feedback loops in your body. An example of negative feedback that requires a conscious effort is threading a needle. This requires very precise positioning of the thread to get it through the eye of the needle. As you watch your effort, if you notice the thread is too far in one direction to get through, you will adjust it in the other direction to try to get it through the eye. In the manufactured world, humans have designed and used feedback systems for millennia. Water clocks are devices that use water flow to measure time, and one challenge of these devices is getting the water to flow at a constant rate. The Greek inventor Ctesibius developed a mechanism for using negative feedback to control the water flow, and this clock that he invented was the most accurate clock in existence for more than 1800 years. And there are countless other examples of negative feedback control in engineering systems. A really simple one is this water level control. When the water level drops below a required level, the spigot opens up to allow the water to flow in. And then once it's filled up, that spigot, that opening for the water, closes. And automated greenhouses are great examples of negative feedback systems where temperature and humidity must be maintained at very specific levels to allow the plants that you are trying to grow to optimally thrive. And of course, more applicable to this YouTube channel, electronic amplifiers, and more specifically, operational amplifiers such as this one are great examples. And op-amps are such perfect mechanisms for using negative feedback because they have two inputs with the output based on the difference between the two inputs. And this is shown in the diagram of the voltage amplifier right here. The simplicity of the circuit allows it to be modeled with this simple block diagram of a negative feedback system. The elements of the op-amp can be seen on the diagram. So the input to this block diagram is V in. This point right here is the non-inverting terminal, so that point there. This point right here is the inverting terminal, so that's that point right there. A, well, that's the open loop voltage gain of the op-amp. The output here, this is V out. And B, this is the feedback ratio that's being fed back into the summing part. So that's going to be based on the external components of the circuit. And you'll have to wait until the video on non-inverting amplifiers to find out what the value of B actually is. So now let's solve this output, this V out output, in terms of V in, the A value for the amplifier, and the B value that's based on the feedback here. So this is V out. I'm going to use B instead of beta to represent what's down here in this control systems block diagram. And I want to solve for V out. And as you may know, the open loop voltage gain given by this A value of an op-amp is very large. So if it's true that this is very large, then this value of 1 is going to be very small compared to the value of A. So with a very large A, we will get V out is equal to A over AB times V in, which of course is just equal to 1 over B times V in. So with this negative feedback, we can create an amplifier that has an output that's proportional to the input. And that constant of proportionality is based on this 1 over B value, this feedback value, which for op amps is based on these two external resistors. And before we wrap up here, I just want to talk about a number of advantages that come when you have negative feedback in an op amp. The first one is that the actual open loop voltage gain doesn't matter much. So the actual value of A right here, it doesn't really matter because the output is really going to be proportional to what's going on outside of the amplifier. Secondly, you get increased stability. If there are external disturbances, the op amp is going to continue operating pretty much as normal. The op amp negative feedback is going to smooth out nonlinearities, and that's going to reduce distortion. The negative feedback increases system bandwidth, and it provides control over input and output impedances. So these are a number of broad claims about negative feedback in op amps. And there are a lot of details that you need to go into to understand how negative feedback affects each of these things. So you're going to need to stay tuned to the channel to learn more. So this has been just a really brief overview of negative feedback, and hopefully it sets you up for a better understanding of negative feedback in op amp circuits. Thank you so much for watching. See you soon.